Good evening, dear students. I welcome you all to this session of today's YouTube. Today, I would be discussing about tooth preparation instruments. So, all of you are aware that every month we talk about a certain topic related to my subject of concern and students. Okay. Myself, Dr. Nitin Kararia, and I welcome you all to this session. So, let us start with the tooth preparation instruments. See, basically, tooth preparation instruments means the various types of instruments, whether they are hand instruments or rotary instruments that we use to prepare the tooth surface for the coronal restoration. So, tooth preparation basically means instruments used in the operative dentistry. So, if we broadly outline two category of instruments we use for the tooth preparation, one are the hand instruments. The second category of instruments are the rotary instruments. Hand operated by the hand, manual instruments. Rotary means some sort of engine driven instruments are used. Let us first talk about the hand instruments used in operative dentistry. See, principally, before seeing the hand instrument, we have to talk about the alloy that is used to make the hand instruments. What material the hand instruments are made up of. We know that tooth structure is quite hard, and to cut it through the hand, it requires a lot of effort and so the instruments that we use for such purpose should be efficient enough to cut the tooth with the hand pressure. So the material wise or alloy wise, two type of alloys are used. One is your stainless steel instruments. Okay. And the second category are carbon steel instruments. Two type of materials are used to manufacture the instruments. As the name indicates, carbon steel, 0.5 to 1.5% carbon is added to steel to make it carbon steel. Now, what is the fundamental difference between these two materials? The stainless steel instruments, when we compare with the carbon steel instruments, they are resistant to corrosion. I am talking about the properties of these two type of materials. Okay, they are resistant to corrosion. They are less efficient. They are less efficient as compared to carbon steel in cutting the tooth structures. They are less brittle. Okay, and they dull faster. The instruments for cutting the tooth structure need to be sharp. But when we are using these stainless steel instruments, they have a tendency that they become dull faster. Now coming over to the carbon steel instruments. Carbon steel instruments have properties like they are more efficient in cutting the tooth structure. Efficient means they are more efficient than stainless steel in cutting the tooth structure. They are also more prone to corrosion. What is meant by prone to corrosion? See, these instruments are multiple use instruments, definitely. So after each use, they are supposed to be sterilized. If we are using some form of moist heat or other forms of chemical sterilization, then the carbon steel instruments are more prone to corrosion as compared to stainless steel instruments. Now, to prevent the corrosion, 2% sodium nitrite, 2% solution of sodium nitrite, it is used as anti-corrosion agent. It is used as anti-corrosion agent, 2% sodium nitrite. It is not nitrate, but it is nitrite. This has been asked in the questions couple of times. What is the anti-rust agent used to prevent the corrosion of carbon steel or tungsten carbide instruments? Answer would be 2% solution of sodium nitrite. They are brittle, means they tend to fracture, and they dull after a long use. because they are more efficient. They can be used longer as compared to stainless steel instruments. So technically, we use two type of alloys, the carbon steel and the stainless steel. Sometimes do not get confused with the carbon steel. To manufacture the dental burrs, which are a rotary type of instruments, we use tungsten carbide. Tungsten carbide. Carbide again means there is incorporation of carbon, which makes it more hard and more brittle as compared to stainless steel. So the properties of whether carbon steel or tungsten carbide, they remain the same. Now we talk about hand instrument design. What is the design of hand instrument which is used? See, these are the prelims and the basics of operative dentistry and NEET examinations. A lot of questions are being asked from here. Hand instrument basically consists of three parts. One part with which the instrument is held is called handle. Then there is a shank and there is a blade. So the three parts of an instrument are handle, shank, and blade. So basically, whenever we are using an instrument to cut the tooth structure, the part is called blade. Blade is used for a cutting hand instrument. Suppose we are using a non-cutting hand instrument. What is a non-cutting hand instrument? Can you think of an example? A non-cutting hand instrument is like ball burnisher or amalgam condenser, whose purpose is not to cut the tooth, but it is used to manipulate the materials with holding the instrument in the hand. So, for a non-cutting instrument, the part corresponding to blade is called nib for a non-cutting instrument. The part corresponding to blade is called nib. And the active end of nib, it is called face. It is for a non-cutting instrument. So I would draw a diagram of a non-cutting instrument. Suppose I talk about a amalgam condenser. Then amalgam condenser has got geometry like this. This non-cutting part is called nib of the instrument. Nib, shank, and handle. Okay. And the active end of the nib, it is called face. So face of the instrument is actually the one which produces the work. So depending upon whether the instrument is cutting or non-cutting, these are the corresponding parts for that. Now for hand instruments, whether they are cutting or non-cutting hand instruments. Okay. One property is required, that is balance of the instrument. The instrument, whether it is cutting or non-cutting, suppose this is the instrument I am using, holding it in my hand and then applying pressure either to manipulate the restorative materials or to cut the tooth structure. So to efficiently do any of these tasks, the hand instrument should be balanced. What is meant by balanced of the instrument? The blade edge should be within 2 millimeters of the instrument axis. It should be within 2 millimeters of the instrument axis. What is meant by this? If this is long axis of the handle, this is the shank of the instrument, and this is suppose the blade for the cutting one or nib for the non-cutting one. This is the long axis of the instrument, and this is an imaginary line drawn touching the edge of the blade or the nib. This distance from the axis should be within 2 millimeters. It should be less than equal to 2 millimeter. This is known as balance of the instrument. This balance provides adequate anti-rotational property to the instrument. So whenever the force is applied, cut the tooth structure or manipulate the restorative materials, such instrument would not rotate in the operator's hand. So there would be no slipping or rotation of the instrument while applying the pressure. And this is done by making an instrument balanced. So balance, it should be within 2 millimeters of the instrument axis. Okay. Now we talk about classification of hand instruments. Two principal category of hand instruments are there. One which are used to cut the tooth structure and the others which are non-cutting, isn't it? Cutting means they are used for tooth preparation, cutting of dental hard tissues like enamel, dentine, and cementum at times. Cutting instruments are further principally of three types. The first ones, they are called chisels. The second ones, they are called excavators. And the third ones, they are others, other type of cutting instruments. Chisels, excavators, and others. What are chisels? Chisels, as the name indicates, their primary function is to cut enamel. Which dental tissue they are meant for? They are cutting instruments. So the hand cutting instruments called chisels are primarily made for cutting the tooth enamel. Chisels, if we talk about examples, there are numerous examples for chisels like straight chisel, straight chisel, curved chisel. Curved chisel is also called Wedelstedt chisel. Wedelstedt chisel. Wedelsteadt. Then we have enamel hatchet. Enamel hatchet. Another example is bin angle chisel. Bin angle chisel. And finally, we have GMT, which is gingival marginal trimmer. So these are 5 examples of instruments called chisels. And what is the primary function? The primary function is to cut tooth enamel. If we look at the example of instruments called excavators, another category of cutting instruments, then you have to remember examples like spoon excavators, hoe excavator. Third example is angle former. And we have ordinary hatchet. So you can see the word hatchet is common with the chisels and the excavator, but ordinary hatchet is a type of excavator and enamel hatchet is a type of chisel. And what are the other types of cutting instruments? They include scalers, carvers for the restorative materials, knives, and files. These are the 4 types of others miscellaneous cutting instruments. So principally, the instruments used to cut the tooth structure can be of 2 types, chisels and excavators, and the miscellaneous ones. Okay, you have to remember the examples of 5 types of chisels and the 4 types of excavators. Non-cutting instruments like spoon excavator, ball burnisher, mouth mirror, etc. They are non-cutting instruments. Now we talk about instrument formula. To identify each of these hand instruments, there is a 4-digit formula which is encrypted on the handle of the instrument. This instrument formula was initially given by Dr. G.V. Black. Okay. Dr. G.V. Black is also called father of operative dentistry. In the 1900s, he was there and he gave the formula called instrument formula. So basically, to represent the instrument and describe the properties, there is a 4-digit formula that is used. So what is a formula? To understand that, I would draw diagram of an instrument again. This is the shank of the instrument, and this is the instrument blade. I have redrawn it to understand it nicely. Now, this solid black line, this is long axis of the instrument. Okay. This dashed broken red line is a line that is parallel to the instrument long axis, touching the blade edge. You can see it is touching the blade edge, an imaginary line that is parallel to the instrument long axis. What is long axis of the instrument? The long axis of the instrument is the solid black line. Then there is a solid green line that is an extension of the blade edge. Extension of the blade edge. And then there is a solid purple line which is long axis of the blade. So what does these lines indicate? This purple line, it indicates the blade axis of the blade. The solid black line represents the instrument axis of the instrument, isn't it? The green line is an imaginary extension of the primary cutting edge of the blade, and the broken red line is a line that is parallel to the long axis of the instrument, that is the black line in the given figure, and touching the blade edge. So these are the 4 axes or the lines that we use to describe the instrument formula. What is the first digit of the instrument formula? It is the width of the blade. It is simply blade width. And this blade width is represented in 1/10 of millimeter. Suppose you take a hand instrument where the first number of the 4-digit formula is 20. What does the first number indicates? It indicates the width of the blade in 1/10 of the millimeter. So what would be the blade width? It would be 20 upon 10. That is 2 millimeter. Okay. The first digit indicates the width of the blade in 1/10 of a millimeter. Second digit of the 4-digit formula indicates primary cutting edge angle. Primary cutting edge angle. To understand what is primary cutting angle, look at the figure that I have drawn again. You can see a solid green line. That solid green line is an extension of the blade edge. So this is basically the primary cutting edge of the blade, and it is represented with green line. So this primary cutting edge angle is measured from a line parallel to long axis. In our figure, what is that line parallel to the long axis? The red line in clockwise degrees. In clockwise degrees. So basically, principally speaking, you have to measure the angle between the red and the green line. in clockwise degrees. So we would start from this, a line that is parallel to the long axis of the instrument, and measure it clockwise. It gives you primary cutting edge angle. I hope all of you understand what is a primary cutting edge angle. It is measured from a line that is parallel to the instrument long axis in clockwise degrees. So you have to measure between primary edge and a line parallel to the long axis. Okay. Third digit of the 4-digit formula simply represents the blade length in straight millimeters. The length of the blade in millimeters. Okay. If suppose the third digit is 15, it simply means the length of the blade is 15 millimeters. It is not in 1/10 of the millimeters, but simply in millimeters. Coming over to the fourth digit, it represents the blade angle. What is angle of the blade? Now, angle of the blade is again measured from long axis of the instrument itself, which in our case, the figure that I've drawn is the black line. It is measured from long axis again in clockwise degrees. Angle of the blade with respect to the long axis. So if I come back to the figure, okay, from the long axis to the blade, this angle between the black and the purple line, this is the fourth digit or the blade angle. Angle between long axis, line parallel to the long axis and the primary cutting edge, this is the second digit. So there are 4 digits in the instrument formula, out of which 2 digits represents 2 angles, and first and the third digit represent the instrument dimensions. The blade width, primary cutting edge angle, the blade length, and the blade angle. This is the 4-digit formula which is used to represent and identify the instruments given by Dr. G.V. Black. Now, there are different types of instruments, hand instruments we have seen. Okay. Principally speaking, 4-digit formula, 2 instruments are there which have a full 4-digit formula. One is an example of chisel, that is gingival marginal tremor, and other is an example of excavator, that is angle fall. Okay. These instruments, you have to remember that they have technically 4-digit formula. All the other hand instruments, cutting instruments, all the other examples of chisels and excavators have only 3 digits in the formula. So when blade edge is perpendicular to blade axis, the second digit is not present. The primary cutting edge angle is not defined in an instrument where the blade edge is perpendicular to the blade axis. If you find it difficult to understand what is meant by being perpendicular to the blade axis with respect to the blade edge, you simply remember that 2 examples of instruments with 4-digit formula are GMT and angle fork. All the other instruments would be having 3-digit formula, and which digit would be omitted? The second digit is omitted in the other instruments. Okay. Now we talk about instrument uses. We have seen different hand instruments. What are the uses for these instruments? Firstly, we'll talk about GMT, that is gingival marginal tremor. As the name indicates, it is used to bevel gingival cavo surface angles of class 2 preparations. What is a class 2 preparation? A preparation which involves the occlusal and the proximal surfaces is a class 2 preparation. To bevel the gingival cavo surface angles of class 2 preparation, okay, a class 2 preparation in a coronal section would be something like this. We place a bevel here. Okay, this is gingival cavo surface bevel in a class 2 preparation. GMT is used. Okay, when second digit, we have seen GMT would be having a 4-digit complete formula. So when the second digit of the GMT is 70 to 95, it is a mesial GMT. What is meant by mesial GMT? I have told you what is the use of gingival marginal tremor. It is used to place gingival bevels in a class 2 preparation. Now, a class 2 preparation can be a mesial occlusal preparation or can be a distal occlusal preparation. So, if it is a mesial cavity, mesio-occlusal cavity, you have to use a mesial GMT. If it is a distal occlusal cavity, you have to use a distal GMT. And how you would identify whether this GMT is mesial or a distal GMT? You have to look at the second digit of the instrument. When the second digit is 70 to 95, 70 to 90, or sometimes it is represented as 70 to 85 more appropriately. Okay. So I would suggest that you stick to this configuration 70 to 85. It is a mesial GMT. And when the second digit, you have to look at the second digit of the GMT. It is in the range of 90 to 100. The second digit is 90 to 100. It would be a distal GMT. So how you can identify whether this is a mesial or distal? By looking at the second digit of the instrument formula. If the second digit is less than 90, 70 to 85, it is a mesial GMT. If the second digit is more than 90 or equal to 90, 90 to 100 is the range, it is a distal GMT. So depending upon this, select the gingival marginal tremor. Now, if you remember about restorative dentistry, we place gingival cavo surface bevels in class 2 tooth preparations both for cast metal and for amalgam. Okay, where do we find the need? We find the need to prepare a gingival cavo surface bevel in cases of class 2 amalgam tooth preparation and class 2 cast metal tooth preparation. Okay, so 85 and 90, they are the GMTs for amalgam tooth. Okay, and 70 and 100, they are the GMT for cast metal tooth preparations. So a GMT with second digit 70 would be mesial GMT for cast metal. Second digit 85 would be a mesial GMT for dental amalgam. Similarly, second digit 90 would be distal GMT for amalgam, and second digit 100 would be distal GMT for cast metal tooth preparation. So this is how, depending upon the restorative need and the material of choice, we can select the gingival marginal tremor. Again, what is the principal use? The principal use is to bevel the cavo surface gingival line angles. Enamel hatchet. Enamel hatchet is another example of a chisel which has got geometry like this. It would be having a handle, shank, and a blade. Okay. Handle, shank, and blade. This enamel hatchet got large and heavy blades. It has large and heavy blades. And this enamel hatchet is mono-beveled. The blade is beveled only in one direction. So it is mono-beveled. These are the two important design characteristics of enamel hatchet. Firstly, the blades are large and heavy, and secondly, it is mono-beveled, which is a type of chisel. So what is the use of enamel hatchet? It is used to plane tooth preparation walls. It is used to plane the tooth preparation walls, to smoothen the tooth preparation walls. Okay. Then we have angle former. I am telling you the uses of principal hand instruments, whether cutting type of chisels or cutting excavators. Angle former is also called a special excavator. Okay. This is basically a hybrid instrument, which is a hybrid of chisel and GMT. A hybrid instrument consisting of the properties of chisel and GMT. Angle form. Its uses, two principal uses of angle former. As the name indicates, angle former, it is used to sharpen internal line angles. It is used to sharpen the internal line angles. And which type of restorative material requires sharp internal line angles of the tooth preparation? It is direct filling gold. So whenever we are doing preparations for direct filling gold, we have to sharpen the internal line angles to help in the retention of direct filling gold, and that is done with the instrument called angle former. The second use of angle former is to place retentive points in dentine. It is used to place retentive points in dentine, especially in class 3 tooth preparations. So these are the certain basics of operative dentistry. What type of instruments do we use and what are their uses? Okay, these are the two principal uses. Then we have another example of an excavator, that is ordinary hatchet. Ordinary hatchet has an important property that it is bi-beveled. Enamel hatchet is mono-beveled. This is bi-beveled. So the blade of the instrument would be something like this. It has got bevel on both the sides. So ordinary hatchet is an example of an excavator, a hand instrument, and it is bi-beveled. Important difference from enamel hatchet, which is mono-beveled, an example of chisel. If I talk about uses of ordinary hatchet are exactly the same as that for angle former. So if in your questions you get which instrument is used to place retentive points or sharpen the internal line angles, then the first choice answer would be angle former. If angle former is not there, it would be ordinary hatchet, because both of them have the two similar uses. So these are the important uses of instruments, hand instruments. Now we have been talking about hand instruments, means we would be holding the instrument in the hand and doing the work, whether manipulation of restorative materials or cutting the tooth structure. Now, what is the method for holding the instruments in hand? So it is known as instrument grasp. How do we hold the instrument in hand is known as instrument grasp. There are 4 ISO recommended grasp. ISO is International Standardization Organization. 4 grasp are recommended by ISO. The first one is modified pen grasp. Modified pen grasp. Okay. I am holding a pen in my hand. This is a pen grasp. When I'm using an instrument, holding an instrument to cut the tooth structure, I would use a modified pen grasp. In modified pen grasp, if you look, I'm using my thumb the index and the middle finger to hold the pen. Okay, but my middle finger is below the instrument. If I keep my middle finger also on the instrument, it becomes modified grasp. Thumb, index, and the middle finger. So, modified pen grasp, the instrument is held between. The instrument is held between thumb, okay, index finger, and middle finger. All three of them rest onto the instrument, and the palm faces away from the operator. The palm faces away from operator. So I would be holding the instrument like this and working in the patient's mouth like this. The palm would be away from me. This is modified pen grasp. This is the most common instrument grasp used in majority of the restorative and tooth preparation situations. Second ISO grasp is inverted pen grasp. Inverted pen grasp. Here again, the holding of the instrument remains the same, that I would be using my thumb, the index, and the middle finger, all three on the instrument. The middle finger, the index finger, and the thumb, all three on the instrument. But I would be working with the palm toward me. The palm faces the operator. Okay. What is the difference? The palm faces the operator or the dentist. Palm away from the operator, modified pen grasp. Palm toward the operator is inverted pen grasp. Inverted pen grasp has got limited applications. It is used on palatal surface of maxillary anteriors. When we are working on the palatal surface of maxillary anteriors, we use an inverted pen grasp. The third instrument grasp recommended by ISO is palm and thumb grasp. Palm and thumb grasp. Okay, what is happening in palm and thumb grasp? The instrument is held between fingers and palm. Okay, and thumb is free of the instrument. The thumb is free of the instrument and it acts like extraoral rest. So I would be basically holding the instrument like this between the palm and the fingers, and the thumb is free of the instrument. This grasp is known as palm and thumb grasp. So we work in the patient's mouth, keeping it like extraoral rest and then working. Okay. And the final grasp is modified palm and thumb grasp. Modified palm and thumb grasp. This modified palm thumb grasp, instrument is held between, again between fingers and palm, just like in palm and thumb grasp. But the first joint of thumb touches the instrument. The first joint of the thumb touches the instrument. So I would be holding the instrument like this. The first joint of the thumb touches the instrument. It is known as modified palm and thumb. This is palm and thumb grasp. Okay. This is modified pen grasp. And this is inverted pen grasp. So these are the four ISO recommended instrument grasp to hold them while working in the oral cavity. This is all about your hand instruments. Now we talk about rotary instruments. Rotary instruments. See, basically, rotary instruments, they would be using a handpiece and a burr to cut the tooth structure. Okay. Burr technically means a bladed cutting instrument. Any instrument that is made up of blades is called burr. This burr, again, material wise, it can be either stainless steel or it can be tungsten carbide or carbon steel. What are the properties of stainless steel and tungsten carbide? We have already seen when discussing the hand instruments. Now, this handpiece is basically the device which transmits the power to the burr. So, this handpiece can operate at low speed or it can operate at medium speed or high speed. These are the three speed ranges which are principally used for rotary instruments. Low speed, any instrument operating below 20,000 RPM is considered to be low speed. Medium speed, 20,000 to 2 lakh RPM. And any instrument greater than 2 lakh RPM is considered to be high speed. This is the single most relevant classification of the rotary speed ranges, low, medium, and high, depending upon the speed of rotation, RPM. So burr principally is the active part of rotary cutting instruments, isn't it? Which does all the work of shaping and cutting the tooth structure during restorative procedures. Now we talk about burr design in greater detail. Burr design. Burr design consists of three parts: shank, neck, and head of the burr. So burr would be something like this: head, neck, and shank. Just like there are three parts to a hand instrument, there are three parts to burrs: head, neck, and shank. As the name indicates, burr, it is a bladed cutting instrument, so there would be blades on the instrument. Okay. So the most active part of the burr is the burr head. And depending upon the head geometry and the dimensions, there are different assortment of burrs available, and we purchase and buy the burrs depending upon their head geometry and dimensions. So we would see the burr head design in greater detail. We will talk about burr head design. Okay. Just to illustrate the example, I am taking an example of a straight fisher burr. This is neck of the burr. This is the long axis of the burr. These are the blades of the burr. So what are the characteristics of the burr head design? The first and the most common characteristic that we use while purchasing the burrs is the head length and diameter. Isn't it? We talk about the head length and diameter. Both these head length and diameter, they are the descriptive properties represented by ISO number on burr. ISO numbering on burr is there, which is basically a 3-digit number. So I think most of you know about this and must have purchased the burr depending upon the head diameter. So the height diameter is principally indicated by an ISO 3-digit number printed on the per packet. It can be 010, 012, 014, isn't it? You must have seen these 3-digit numbers. What does they represent? They represent the diameter of the burr head in 1/10 of millimeter. So you divide by 010 by 10, you get 1 millimeter, 1.2 millimeter, 1.4 millimeter. They are the diameter of the burr head represented by these 3-digit ISO numbers. Okay. But these head length and diameters, they do not influence the cutting efficiency of the burr. What is cutting efficiency? Amount of energy that actually produces the cutting of the tooth structure. See, I have mounted a burr in a rotary handpiece which can be operating at low, medium, or high speed depending upon the work at hand. So, efficiency means how effectively the burr cuts the tooth structure. Depends upon the amount of energy being transmitted to the burr, and these head length and diameter do not influence the cutting efficiency of the burr. The second design characteristic is taper angle of the burr. Taper angle of the burr. Okay. If I talk about another design of a burr and extend these two edges of the burr, they would imaginarily meet at an angle which is called taper angle. The two edges of the burr head, when they are extended, they would meet at an imaginary angle which is called taper angle of the burr. But this taper angle of the burr also does not influence the cutting efficiency. This also does not influence the cutting efficiency of the burr. The next parameter is spiral angle, which is also called helical angle of the burr. Spiral angle or helical angle. Okay. This is the angle between long axis of the burr and burr blade. Angle between long axis and the burr blade is called spiral or helical angle. The angles marked with green, they are called spiral or the helical angle. You can see they are present between the long axis of the burr and the burr blade. Okay. Cutting efficiency of the burr. CE stands for cutting efficiency is inversely proportional to its spiral angle. Smaller the helical angle or the spiral angle of the burr, greater would be its cutting efficiency. CE stands for cutting efficiency of the burr. So what is the parameter in the head design which is influencing the cutting efficiency? It is the spiral or the helical angle of the burr. Okay. The fourth characteristic is cross cut. Cross cut. Cross cut blade. Now we know that there can be two type of burrs depending upon the blade geometry. One has smooth blades, which is called plain cut. The blades of the burr are smooth. In another case, the blades are serrated or dimpled like this. Okay, the blades are not smooth. These are called cross cut blades. So burrs can be either plain cut or the cross cut depending upon their geometry of the blades. The cross-cut blades, they are more efficient. They are directly proportional to cutting efficiency of the burr. Okay. And plain cut burrs, they are less efficient, but they produce a smoother surface. Cutting efficiency of cross-cut burrs is high, but they produce a rough surface. Isn't it? Because of dimples present or serrations present in the blade, they would produce a rough surface. So smooth surface is produced with plane cut, but they are less efficient in cutting the tooth structure. And rough surface is produced with cross-cut burrs. Cross-cut means there are serrations in the blade of the burr, but they are more efficient as compared to plane cut burrs. These are the different characteristics of the head design which influence and which do not influence the cutting efficiency of the burr. Okay. Now we study the burr head in cross section. Head of the burr in cross section. There can be three clinical situations. We can have blades with three type of designs. Okay. If I make a cross section of the burr head, this is the circular cross section of the burr head. And if I look at the geometry of the blades, there can be clinical situations like blades are like this. The blades are like this. I'm looking at the burr in cross section, okay, from top, and I see the blade geometries like this. So any of the three type of blade designs can be present on the burr. If we look at one blade of the burr in the three clinical situations, okay, we are looking at one blade of the burr in the three situations. Then this is the tooth structure against which the burr is rotating. This is the center of the burr head. This is a straight line that is called the radial line, and the burr has a design like this. Isn't it? The blade has a design like this. In the second situation, this is the center of the burr head, radial line, and the blade has a design like this. In the third situation, center of the burr head and the blade has a design like this. Isn't it? These are the three types of design that can be incorporated in the burr blade. The burr, when used, rotates in a clockwise direction against the tooth structure. Then, when the burr is rotated, the front face of the burr blade, this is called rake face. The front face of the burr blade. The back face is called clearance face. So in this situation, this would be the rake face of the burr. This would be the clearance face of the burr blade. In the third situation, this would be the rake face of the burr blade. This would be the clearance face of the burr blade. Okay. So depending upon which edge of the burr is in front, it is called rake face, and the back one is called clearance face. Now, if I look at the rake face and radial line, there is an angle between the rake face and the radial line. This angle is called rake angle. So there is a rake face and a rake angle. Here, the rake face is coincident with the radial line. So this technically has a zero rake angle. In the third situation, if this is the radial line, this angle again would be rake angle. So when I'm talking about the head of the burr in cross section, when the burr rotates, the blade has got a front face, which is called the rake face, and a back face, which is called clearance face. Depending upon the angle which the front face of the burr blade forms with the radial line, it can be called rake angle. This rake angle is a negative rake angle, the first situation. The second situation, I have already told you, the rake face coincides with the radial line is a zero rake angle. And the third situation is a positive rake angle. So burrs can be manufactured in either zero, positive or negative rake angle. When the rake face is ahead of the radial line, as you can see in the first diagram, the rake face of the burr is ahead of radial line. It is called negative rake angle. When the rake face coincides with the radial line, it is called zero rake angle. And when the rake face is behind radial line, it is called positive rake angle. So if you look at the three design characteristics, which type of burr design you see would be the most aggressive in cutting the tooth structure? Definitely scenario 3 would be the most aggressive in cutting the tooth structure. So more positive the rake angle of the burr, more highly efficient it is in cutting the tooth structure. So what we can conclude, cutting efficiency of the burr. The cutting efficiency of burr is directly proportional to its rake angle. More positive the rake angle, more cutting efficiency there would be. And the similar concept applies to your endodontic instruments also. We have seen that H-type instruments that have got positive rake angle are more effective in cutting the tooth structure as compared to K-type instruments with slightly negative rake angles. So a burr can be having a negative, zero, or positive rake angle, and similarly it can be having a high cutting efficiency or a low cutting efficiency. Now there is an influence of the characteristic of the alloy type. We have seen that tungsten carbide, or simply I would say about carbon steel instruments, they are more efficient in cutting the tooth structure, but they are made with slightly negative rake angles. They are more efficient in cutting the tooth structure, but they are manufactured with slightly negative rake angles. What is the reason for this? Because they are brittle. And if you look at the design characteristic, if I come back to the figure, you can see that a brittle instrument made with a positive rake angle would be having too thin of an edge for a burr, and it is likely to fracture. So what you have to remember that carbide, because they are more harder as compared to stainless steel, are inherently more efficient in cutting the tooth structure, and cutting of tooth structure by a rotary instrument is directly proportional to its rake angle. But when it comes to carbide instruments like tungsten carbide burrs, they are manufactured with a slightly negative or zero rake angle to prevent the burr fracture. This is the concept of rake angle, and it is applicable to all types of cutting instruments, whether they are dental burrs or whether they are your endodontic instruments. Because basically endodontic rotary instruments also work on the same principle of cutting the tooth dentine inside the root canal. Okay, so these are the design characteristics of your rotary and the hand cutting instruments and the important properties. With this, I conclude today's session. See you next month with another topic. Till then, happy reading, enjoy your studies, and perform well. Thank you very much. I am signing off with this now.